Hey everyone. Let's see, we still have like a minute or so. We'll give everyone a chance to get in. How's everyone been for the past 2 weeks? End of semester grind?
Yep, yep. Hey
Yep.
Dan, have you chose the can I ask I'm gonna ask a
Yeah.
question. Have you
Yeah, go
chosen
ahead.
the people, the students for Iriva this year?
Yes, I have. Notifications went out 2 weeks ago. 20 of the 21 accepted. So I sent a final notification out yesterday. It was tough. We had 80 applicants, so it was 4-to-1
Wow.
oversubscribed. It's
That's
usually 2.5 to 3 to 1 oversubscribed. This was 4-to-1.
wow. That's great news, I would think, isn't it?
Yeah,
Wonder if is it because REUs are not something people are confident in?
it could be. It could also be because my email list is getting bigger due to all the Opus trainings and MWU stuff. So I send it out to more people. That could be part of it. We do get a lot from ASU online, and usually one ASU student makes it, but it's usually one of the ones that are on campus. So it's a little tougher for the online students to make that bar. Another aspect is I always kind of split them 50-50 between UNC and non-UNC, but I have to do it like two-thirds UNC now, two-thirds, three-quarters UNC, uh, just so it continues to count for my teaching. There's a minimum enrollment, and I like that it counts for my fall teaching. I don't have to come back and do another class. So accepted more UNC students this year. But in fairness, looking at their applications, they earned it. And often in previous years, the final UNC ones that make the list, there are probably one or two non-UNC students who would have beaten them if I wasn't maintaining the 50-50. But this year they had very strong applications. Anyway, let's see. We are past 3 o'clock, so I think we have the group that we're going to have. It's great that we're this far into the semester and we still have like a full Zoom screen. That's great. Often kind of withers away with time. And these will keep going for a few weeks, probably through most of May, if you want. It's totally up to you. Just because we still have, like today, we're doing Module 5B, and then we'll do Module 6. Both are short modules. Both will be 1 week things, I think. And we'll do Module 7, which we'll probably also do in a week, though that could go to 2. And then we'll cycle back and do Module 5C, which is new. It's a gravitational wave module. Clay's worked up a version, though. I'm going to do a slightly different version and see what she thinks about it. So we did complete building the gravitational wave tool in the new Astromancer framework. So the old one is retired. As soon as we just get this thing hosted on the server, it's just a matter of Reed setting it up. But the new one should be there and should be able to handle lots of simultaneous users. I'm pretty excited about it. But we'll end with that one. All right. So let's see. I'm looking at my list. Couple notes. I learned that Opus students have been watching our Opus training videos to get the answers. So I've now made them not public facing. You have to have the link for the collections. We do Opus training every fall, and so there's a bunch of previous collections. So that was insightful. I think my undergrad TAs for the MWU course for alerting me to this. And probably our playlist here, I'll make it not public facing by the end. But I'm less concerned about MWU students cheating, right? They're producing blogs and there's no right answers. But okay, so that's one announcement. Then also, I'm gonna share my screen. Uh, okay, move you all over here. Spread you out. No, spread you out. Move you around. There we go. I attached this to the email. I spent like a day and a half working on this. I'm real pleased with it. You remember a couple weeks ago, we did Module 4A, which is We just developed it this past year. I'm not sure why it was one of the last modules developed. It should have been one of the first because this is kind of the primary project we do at Arira every year, and MWU is based on Arira in part. But this is where, after their, just talk about radio stuff. They have a few introductory tastes with the moon and Jupiter, but this was the first serious radio project where they divvied up this, a good chunk of the sky, the galactic plane mostly, and just remembered that at some point I'm going to have to unshare and reshare and enable the sound for the pulsar module. Just make a little note there. Okay. Anyway, they divvied up the sky, and each team did a separate piece, and then we put it all together into this large map and also large source catalog. So I spent last weekend going through their blog entries and just using the tool myself, being really obsessive and nitpicky, trying to identify every little blob of radio emitting light, radio waves. And to do 16 of these projects back to back, it took all day. And by the end, my mind was pretty numb and I was just dreading opening another map, but really excited with the result. And so I'm having it printed out as a 10-foot poster that I'm going to take to the final exam period tomorrow for my students. They're not getting an exam, they're doing the capstone activity for Module 7, and they're all going to sign it. I'm going to put up on the wall in our physics building. But yes, can I zoom in? Yeah, yeah, it's pretty cool. I mean, all sorts of stuff in here. Kepler supernovas there. Anything with a common name, I labeled as that. If it didn't have a common name, I just labeled it like star forming region or supernova remnant. I identified all these blobs along the plane. Uh, some galaxies with active galactic nuclei, quasars. This is looking down our arm of the galaxy, so we get this concentrated region, Cygnus A, all sorts of famous nebulae. I love how the elephant's trunk nebula looks like an elephant's trunk. It actually worked out there. Uh, some of these regions are bigger than the resolution of our telescope. I never really realized it, but like elephant's trunk and the question mark nebula, I just thought it was bad processing in the radio, but it actually looks that shape in the optical. California nebula looks like California in the optical anyway. All sorts of good stuff. Heart and soul are two common astrophotography targets. And then once you get kind of anti-center, you pick up lots of galaxies, Seyferts and AGN and quasars and radio galaxies. Crab, Horsehead, Barnard's Loop, Flame Nebula. And then this region doesn't actually sit here. It sits way, way up to the left. I just moved it so I wouldn't have a bunch of blank white space, but that's the center of the Virgo cluster. And all these are active galaxies. Anyway, the other cool thing about this is it serves as an answer key if you do this with your students. And I was brainstorming with Rachel last week. She came out to visit, and we're starting to come up with ideas for the new proposal that will go to whatever's left of NSF this summer. And kind of one nifty idea is, some of you are at small schools and you're teaching small classes, and you can't do the whole map, right? If you're working in teams of 4, you may only have a handful of teams, but we could do partnerships across institutions for this and for a number of things. That would organize kind of informally during these meetings, and so it's a nifty idea. Anyway,
Hey Dan,
yeah, please.
I just popped a link in the chat. Is there any way we could correlate the picture that we're looking at to stuff in the optical? That would be so cool because
Yeah.
then you'd have that sort of connection.
Yes, that's a great idea. It should be fairly easy. We just got to get one of these things like the what's it? We explored it previous couple meetings, the Skyview Virtual Observatory or some tool like that to spit out a good chunk of the optical sky in galactic coordinates and grab this piece of it. And if we do it right and get it to scale, we could blink between the two.
Well, did you see the link? They have one
Oh,
that
good.
looks like
Yeah,
it's
I remember
the, like
this.
I feel like I want to put like I want to
Yep,
correlate it, right? To the map that you've made with your students. That would just be really neat to be
yep.
like, here's what it is in visible and then
I'll do it approximately right now.
nice.
This should be, I'm assuming that's the galactic center right there.
Maybe, yeah.
It's right here. I'm assuming. Let's see. Oh, where's that the center? That's probably the center. So yeah, that's got to be the center. This whole thing is essentially the same size. Let's do this again. Okay. And bring this up and bring, let's see. You always have the best ideas, Clay. Let
Maybe
me
work for other people. That's my specialty.
make this one a little bit bigger. Can't quite fit them both easily, but let me just slide this one down. Okay, so that's, I've now made this too big. Let me shrink it a little bit. That's about right. So here's the center, working along the plane. This region here, you see I don't have any names, just SNR and SFR. It's because it's behind so much dust, they're not optical targets. But over here we have serpents, eagle, and then kind of the middle of the plane. I'm pretty sure that's the serpent, that's Eagle Nebula right there. So these three are probably those three. And these two here, these two. Um, this is probably the Lagoon Nebula right there. But this region here, it's hidden by a dust lane, so there are no common names, which is kind of cool. Looking down our arm of the galaxy, this big messy region's this messy region. And you have things like the North America Nebula in here. And some things are just in the radio, like Cygnus A. It's not a bright optical source. It is an optical source, but anyway, if you zoomed in, you could probably find like the Butterfly Nebula in there. Let's keep going. Here, right here, the Veil Nebula, Eastern and Western Veil. It's right here, Eastern and Western Veil.
Oh, wow.
Yeah. And let's see. This was Cass A, which is, you can't really see it very easily because it's behind a lot of dust. But these little blobs above it are probably the Lion and Wizard Nebula right here. And that's probably Elephant's Trunk, I'm guessing. And then right over here is probably the question mark nebula. In fact, it even looks like it at this scale, the question mark. Yeah, this is fun. Okay. Here's Andromeda. I was thinking about extending the map down to pick up Andromeda, but it's a ways out. Something here. That's got to be a supernova remnant or something. What else? Heart and Soul right here. Here's the Heart and Soul Nebula. And right next to it is Fish Head. So this region right here is this. Fossil Footprint Nebula. And this has got to be California Nebula right there.
Oh, wow.
Yeah. A lot of these are extragalactic source, get active galaxies, so they won't appear super bright in the optical. But yeah, I'm not sure. Yeah. Let's keep going here. This, of course, is Barnard's loop right here. And our background subtraction runs up down. It's kind of canceling out this part of the loop. But here's Orion, Horsehead, and Flame. Orion, Horsehead, and Flame's all in here. Up here you have the rosette right there. And Jellyfish Nebula is probably this. The crab's around here somewhere, but that's not exactly sure. It's got to be something like this, maybe. And then this stuff's not even on the map because there's not as much there. But yeah,
Mhm.
there you go. Just kind of
That's awesome. That's so cool.
winged
It
it.
looks so different. It's amazing to look at the differences as much as the similarities, more than the similarities
That's a
even.
great idea. And so maybe in a future version of the tool that we built for this, we'll eventually incorporate that into Skynet 2. It'll be not a standalone, but just a feature of Skynet 2. And we already bring up optical maps through, well, I kind of never remember the name, Aladdin Light in Skynet 2. So you can imagine the tool having like flipping back and forth to the optical. Yeah, cool. All right. We've had enough time off target. Let's get back on target. Okay, so this is the Pulsar module. Yeah, here it is. Here's the module guide. I'll put it in the chat. And this is the first one the MWU groups developed. If you're a part of the grant from the beginning, you remember spending a lot of time working on this. And there's a different version developed by the educators. This is the version I do with my students. It's a little bit different, but has very many things in common. But anyway, the basic idea, well, actually zooming out just for a second, backing up. In radio, there are four things you can do with your students. There's mapping, and we just talked a whole bunch about mapping, and timing, which pulsars are great for. That's kind of the point of this module. Polarization, which is a trickier concept, but we do touch on it a bit in this module as well. And then spectroscopy, which we'll do next week. And the spectroscopy is great because it's difficult to do spectroscopy in the optical. Difficult to have the instrumentation and know what to do. In the radio, it's easy and automatic. So we tackle all four of these things in MWU. So today is timing and also polarization. So I'm down on page 5 here, and I have a list of pulsars. And these were chosen by the radio group a couple of years ago now. We have 0329, which is the easy one. This one is, pulsars, they don't pulse all the time. Sometimes they're on, sometimes they're off. 0329 is almost always on. The pulses are strong. Though when I did it with my students this time, it was off. And they actually had to resubmit their observations. Then it turned back on like the next day. Uh, anyway, we'll start with that one today. And then what I do is I tell each group put in an 0329 observation, and then each student picks one from the rest of the list. So the list is 5 and 4 people on a team, so they do 4 out of the remaining 5, and so they'll have one of their own. And these, you can see the difficulty level. Usually about half of them work out. It's in the on state, and half don't. Some years I've had like all but one, so it varies. So we're going to start with 0329, and then we may play with a few others. So to do this, go to Skynet. Everyone should do this. And so you'll analyze your own pulsar data. You don't have to watch me. You can watch me and do it. It's really easy. And go to radio observing. And we're not going to submit observations. That's easy enough. You can watch the videos if you do it with your students. We're just going to steal some observations. And that's a whole thing that we're going to emphasize more and more as MW becomes older and has more years under its belt. All sorts of archival data, optical and radio, are accumulating. And some people can run this course just instead of observing to collect data, you just grab it archivally. And then it's totally free. No, I mean, MW is free anyway because we're not charging, but it does cost time. I actually added up how much time just my class of 100 used. It was $22,000 worth of time. Now, of course, then it's phony money, right? I own the printing press, so it's no one had to write a check. And same with you all. We're running MWU at no cost to everyone, and if that will continue if we get this next grant. If not, we'll come up with some kind of strategy. Anyway, come here, click on collaboration observations, so you can search the whole collaboration. Type in PSR 0329, search on that, and you'll see a bunch of them there. And I tested the first one, before we met today. So for all of them that we do today, we'll just go to the first one because I tested it. I got some that examples of things that work and examples of things that don't work. So this is someone's observation. It's from, I don't know, that's the catch-all group. Oh wow. Okay. So this was clear detection. In fact, this one only went 60 seconds. The students, so when we search, we get not just our students' results, but anyone else who happened to do this. And so someone happened to do this. The students do a 3-minute observation on each pulsar. Here's someone who did a 60-second, but the pulses are so strong we can actually see them. And that's not always the case. With the other pulsars, they're pulsing, but it's lost in the noise, and we have to use Fourier techniques to pull it out. This is like the best case of a 329 I've ever seen. The pulses are screaming bright. So let's do this one. What you do is you go up to Continuum, right-click on Calibrated, and just save the link. It's a text file. I'm going to put in my downloads. And some browsers make you press the keep button there. Just show you, it's just a text file. It just has information. This has been integrated over all the frequencies that they looked at. But okay, save it. And then you want to go to our old tool. We're still trying, it's the last thing we have to port over to the new Astromancer framework. My students worked on it, but there's still some bugs. And so here's the old tool. As soon as this gets ported over, the old tool will either be retired or at least no longer maintained. You go there and then go down to Pulsar. Apparently the code base for this is just god awful because it was written by like 5 students at different times, all as their starter project. It is the worst code base ever, but the tool works very cleanly. I'm very happy with how it behaves, but it really needs to be rebuilt and it's almost done. So you go here and just upload that file that you downloaded. And this one it's ridiculous, right? You can zoom in and you can measure the period just from the data here. There's a timestamp and here's a timestamp and we can subtract them and it's about 0.7 seconds. Oh, I'm going to stop sharing. This was the note I made to myself, and then I'm going to reshare and I'm going to press the share sound button. So there's also sonification. You hear it? So it's so strong you can hear the pulses in the raw data, which is not the case usually. Okay. Something to note on this page, it takes the data and it does a background subtraction. Basically, over a certain background scale, it's by default set to 3 seconds. It'll find the median value and subtract that out. For the periodogram to work, you have to subtract out the background. Sorry, it's a former student of mine. He's baking his first cake and he's very excited, sending me pictures. If you hear the dinging of my phone. Anyway, oh my God. Let me turn this off. Okay. We'll tune this. Ideally, you want the scale to be just a little bit longer than the period, but we got to find the period first. So, okay. Well, in this case, we can measure it from the light curve. It's like 0.7 seconds, but we'll do it the way you normally do it. So you go to periodogram, and there's a compute button. And this doesn't compute automatically because this is kind of a slow process, and we want to make sure you're all happy with the settings. So this one, super clean. Normally all this little junk here is stuff, we're looking for the signal in the junk down here, but it's super strong. So what are we looking at? This is not a fast Fourier transform. FFTs require evenly spaced data and 2 to the n points. That's how you make them fast. This is something called Lomskargel. I forget if it's Lomskargel 1 or 2. They're different versions that do different things. But Lomskargel works on data that's not uniformly distributed in time. Even though tried to collect the data relatively uniformly. It's not, the data points come back as they come back. There are slight variations. Anyway, this is power and this is period. So there's a lot of power in this light curve signal on a period of 0.713 something seconds. And we'll zoom in and get a better measurement. Now, what's all this stuff here? Well, zero point 0.7 divided by 2 is 0.35. So that's the first overtone. 0 0.7 divided by 3. Yeah, there's the second overtone. Next overtone. These are overtones. So, if you have some period, it gets, Blum-Scargill also picks out the half period, the third period, the quarter period. In fact, if we put it in frequency space, it's an option. We don't really use it in the module. But instead of period, we can plot this as a function of frequency. You can see they're evenly spaced in frequency. So these are all overtones going all, except for there are a couple of little ones like here at high frequency. And so that's some other, maybe it's RFI, something. And it goes all the way out to the Nyquist frequency. So we're detecting overtones all the way up to the sampling scale. Oops. Let me put it back on period. Okay, so you're kind of looking for the strongest signal to the right, but you got to be a little bit careful because there's once you get to the long periods, there's also noise, and it's not a big deal with this data set, but will be for others. So about 0.7, and the power here is a little bit above 100. So the idea is you go back to the light curve once you know the period and pick a background scale that's a little bit longer than the period. You see all the data adjusted, and that will just bring out the signal more. See, now it's up to it was like one in a little bit. Now it's around 110. So it's a way you can strengthen the signal. It's a minor thing though. It also wipes out any signal above whatever I stuck in there. So above 0.8 gets suppressed. So it's around 0.713. So I'm going to zoom in here and hopefully you're doing this with, hopefully you're following along at home. So I zoomed into between 0.7, 0.73, so I can get a more precise measurement because we need to kind of know it to 4 decimal places. It's that sensitive. So 0.7146. Okay, now that we know the period, is everyone with me? I don't want to go too fast or anything. Okay, now that we go to the period, now that we know the period, we go to the period folding page and enter it in there, 0.7146. And this will take a little bit of time explaining with your students. The version, we do this in Opus as well with our Lyries. And that version's kind of nice because they can actually adjust, as they adjust the period folder, they can see the data points folding on top of each other. We designed it that way so you can teach period folding. Can't really do it with this one because we have to do averaging as well. And so it's binned up. We have 100 bins here. And sliding the slider, you can't see data points move because it's been binned. So you kind of have to explain what's going on is you're taking the data, you're chopping it every 0.7146 seconds, moving all the data on top of each other, and then averaging. And you can see how strong the pulse profile gets. Now, by default, these periodograms show the data set twice. This is not 2 pulses. This is the data, but it shows it twice. It just repeats. That way you get I don't know, it's just kind of convention in the field. You can slide it around if it didn't land where you want. And there are, of course, titles and label axes. You can put that stuff in and save the graph. And makes the student sign an honor code pledge, same as in Opus, so you can check that. So you can resonify it here. And that is cleaner. You may not recall, but the first one had a little bit of static. But again, this pulsar is crazy. The other ones, you go from something that's like all static and you pull it out of the noise and you can hear it. So that's the basic functionality. And if you just want a little taste, that's all you really have to do. Like you could integrate this in a lecture course and everyone does this from their desks. But we can get a little bit fancier here. we could talk about polarization. So you notice we have, let me pause. Any questions about this? Okay, pretty straightforward so far. Okay, we have two channels. So what are those two channels? Up in the receiver. So you have the main dish, and up here in the receiver, it's really two metal bars. The radio waves bounce up and pass through these metal bars. And they're each 1/4 of the wavelength long. And as the waves go through, it induces oscillations of electrons in them. That's an AC current that we can then detect. And if the light is unpolarized, the light's a wave and it's coming in on all sorts of orientations. From photon to photon to photon, they're all different orientations, and it averages out, and you get as much signal in one bar as the other. So for most things, unpolarized things, this is really just a redundant system. But if it's polarized, even just a little bit, let's just focus on the component that's polarized, it'll be at some angle. And so you get a certain amount in one bar, a different amount in the other bar, unless it happens to be on the 45. Then you can by chance get the same amount in both bars and it looks unpolarized. But normally it'd be different amounts, and it's polarized. And what causes this? And in the module, we go through this in greater detail. There are videos. I should say for all the modules I've completed, I now have complete sets of videos after this teaching this year. So all the videos are complete now. So synchrotron radiation, we talked about this back with Jupiter. That's when you have the electrons cycling around a magnetic field line, emitting, because whenever you deflect a charge, it decelerates and emits radiation from Maxwell's equations. Pulsars, it's almost the same thing. There's there are two things going on. There's the cycling around the field line and moving along the field line, which is curved, which causes the electron to deflect as well. With pulsars, the motion is actually more along the field line. You see this little line, it is cycling around, but on a longer scale. And so most of the deflection is due to the curvature of the field line instead of cycling around the field line. It's a subtle distinction. Both are just magnetic field induced radio waves. Most of the things we look at in the radio sky are synchrotron, but with pulsars, it's technically curvature radiation. So the basic idea is, here's the magnetic field, it's off axis, and look at these field lines coming in here, the main cone, or going out. So I'm going to be the pulsar, and here are the field lines, and I'm going to sweep by. So at this point, the field lines curve this way, so you get one type of polarization, and on the back side of the pulse, curve the other way, and so you get a different polarization. So the polarization will change going across the pulse. So even if it happened to be at the 45 on the front of it, it's going to change away from that, and you will see more signal in one channel than the other. And that is confirmation of this whole picture of magnetic field driven radiation. Yeah, it's definitely not thermal. Thermal is in Bremsstrahlung, they're randomly oriented, no polarization. So to see this, it's kind of hard to see. They look kind of the same. You can zoom in and say, well, wait a minute, one of them is kind of leading the other. But what we have the students do is just take the difference. Now we're going to have to calibrate this before we draw conclusions. These two channels, the levels are not carefully calibrated with respect to each other. But if they are, and we'll make them that in a second, then you take the difference, and if it's unpolarized, it should cancel out. And you see the noise level, and there's definitely a signal here above the noise level. But we got to figure out the calibration. But I should point out that for any calibration you choose, the calibration is how much we're going to multiply the second channel to make it the same as the first channel. But for any calibration I choose, I can't get rid of that. So you could stop there and not even need to calibrate it. There's confirmation there that this is polarized signal, and hence magnetically field driven. Well, I'll pause there. All that makes sense?
It does, but I have one question.
Please.
The magnitudes from the raw light curve, the magnitudes of the pulse were varied quite a lot, like the amplitude, I mean.
Yep.
So this is only significant because it's over lots and lots of pulses, right?
Yep. It's been averaged.
I
Um,
see.
but presumably the structure, including which one leads the other and by how much, the polarization is the same from pulse to pulse, at least over this short period of time. And yeah, so the data
Is
that we're
there
averaging is all different levels, but once you
that
average it, the shape is,
that Yeah, I got it. That makes sense. But is there any significance to the changing amplitude? Is that something people study, or is it kind of you look at the average because there's so much variation there, and so when you see a difference in the average, you're like, okay, that's definitely significant.
yeah, people often look at the average because sometimes it's just hard to detect individual pulses, as we'll see as I bring up the next one. And there is significance to the change, but as I understand it, this is still very much an open question of why the pulses turn on and off and why they vary. There are a number of extremely empirical models, like I think a spark model it's called, where you model the pulsars having 12 hotspots around the top, and it's weird, just random stuff. Uh, Astronomer at UNC, he studies pulsating white dwarfs and tried to build a neutron star model where the amplitudes are tied to pulsations in on the neutron stars. And I don't know, I like the model, and it was a very clever paper, though I don't know if it caught on in the field or not, if they just stuck to their empirical kind of made up models. But anyway, yeah, it means something, but we don't know what. Okay, how to calibrate this. So, what we do is we just pick a source that's not really polarized, and really to calibrate this, we'd want an unpolarized pulsar, but there aren't any. So we pick a source, a bright source that's not really polarized, and we do a daisy pattern over it, loop-de-loop. So every time we cross it, the signal is going to go up and then it's going to go down. We're basically faking a pulsar. And so let me give you all a data set here. Where is it? Here it is. This is Cas A, the supernova remnant, where we did 4 loop-de-loops over it. And it looks just like a pulsar now. But it's in the two channels, it's relatively unpolarized, so we can use this data to figure out how much to multiply the second channel by. Actually, and you kind of have to collect this around the same time as your data. This was collected a couple weeks ago. It's probably close enough. And I tell the students to do this in a second. Um, don't close out of this. Leave that there because we're going to want to come back. So you open a new tab. And you can either do this along with me or just watch, and I'll get the number and save some time to do some other things. So I'll do it kind of quickly. I'm going to open up, let me download that data. I'm pretty sure I already downloaded it. Let's see here. No, I didn't. So where was it? It was here. Download the calibrated. I'm going to open up the fake pulsar. Now this was looping. We set it up to do 4 loops in a minute. So it should be about a 15-second period. So I'm going to set this to be just a little bit bigger, 16 seconds. There are the pulses. Pulses that every time we swept over it. Periodogram, we'll have to modify this to go out to, let's say, 20 seconds. So there's the signal and the overtones. And indeed, it is around 15. It's like 14.6. Yeah, just tweaking it. So something like that. And then I can actually turn the difference on here and slide the calibration slider till the data matches up. The difference is 0. maybe something around 1.13 is the proper calibration. And calibration, I'm sorry, you can't make it exciting for the students. Calibration is boring. It is. And students have a hard time wrapping their mind around calibration, but sometimes you just need to do it. If you want to avoid that part, you just tell them that, for their data set, 1.13 was the calibration. It's how much you got to multiply the second channel so it's on the same level as the first. And indeed, the difference then is significant. You can see the polarizations changing across the pulse. Let's do a trickier one. And we can use this calibration constant for all of them. Once you do it once, you can use it for all of them. So let's see. I'm going to go to Skynet. Going to back up collaboration observation, PSR 0950. Search on PSR 0950. Rockenbeck. This student is at American University. Any of you? I can't remember. No. Okay. Let's check this one out. This is what you typically see, right? You don't see pulses in there. Though these little high points those might be the pulses. So go ahead and grab this one. Save link as. Keep it. And I'll go back here and I'm going to upload that data set. Okay, looks like noise. Let's listen. Okay, so that's typical, but there could be pulses in there. It's just hard to say. So we're going to go to the periodogram. Let's see if the power of Lom-Scargill can find it. And so be cautious of this high period stuff. You're looking for kind of significant pulses by themselves. So this is kind of a marginal case, but I'm guessing this is it. Nope, that's not it. Yeah, that's it. So when teaching this, it's important that the instructor and any TAs have the answer key right here. And because you're going to have to help them. It's not always obvious. This one's a little bit more marginal. Usually it's something kind of in between what we just saw and something like this. But this one's not terrible. We got a big pulse right here. Normally, if there's a big pulse there, I'll say, okay, what's double that? Just in case it's an overtone, 0.5, but no, I'm not seeing anything there. So that's probably the primary period right there. 0.25. There's a little hint of something here at 0.3. So let's go out here to back to the light curve and do a 0.4 second background subtraction scale. And then recompute the periodogram. See, it suppressed all that high period stuff. And it's usually the highest peak there. 0.2528. Zoom in, maybe 0.23 to 0.27. Compute. 0.2531. So got a period folding 0.2531. And I forgot to mention this last time because the signal is so strong, but I normally just test. I go down 1 unit in the 4th digit and see if the signal gets stronger or worse. I think that went down 0.3. Yeah, that's almost 0.5. That went down. So you see how sensitive it is. You gotta really line it up. You could probably even tune it at the 5th decimal place if you wanted to get greater precision. And I'll look at the difference. Let me put in my 1.13. And so I can't claim polarization. This was a much fainter, at least I see the pulses, right? You listen to the previous light curve. So by finding that right period folding it, averaging it, we brought the pulses out. You can hear that thing. Now remember, that's about 1.4 times the mass of the sun, the size of any small town USA, a small town anywhere, and spinning this fast. You may want to spend some time just emphasizing the extreme nature of this to your students because it's remarkable to think about. Um, okay, let me show you another example where where it fails, but you can, if you know the answer, you can recover. And you can follow, you can grab this if you want, follow along, or just watch. It doesn't matter. Here's one, and every pulsar is different every time you do it. Sometimes ones fail and then they're good the next time. What was this one? This was 2021. So I tried this one before our get together. Nope, 1 second. That was a daisy. I'm going to do the track right here. So they got 3 minutes of data. Don't really see anything, but who knows? Worked last time. Save link as. Save, keep. Come back here. Upload. This one has a period of like half a second, but it's just totally off. I'll compute it. Now there's some kind of strong signature there at 0.26. That's the overtone. Let me go to my cheat sheet. Yeah, that seems to be the half period, but I'm not getting any signal on the full period, 0.529. Yeah, just nothing. So I can come back here and try 0.6, see if that brings it out. But I've already tried this. I know it's not going to work. Yeah, I seem to be getting the half period, but not the full period. So anyway, 0.52, let's see. So what you could do if it's pretty much in the off state, you can't extract it, 0.5292. If you know the answer, type it in there, you can find it. And let me try 3, that's less. 1, that's less. Yeah. So it's there. It wasn't strong enough to pull out of 3 minutes of data. If I had like an hour of data, then the statistics would have been stronger, but it'd be more expensive. And so it's here. And it's polarized. It's funny, we couldn't bring out the period, but the polarization was actually very strong on this one. Anyway, they go through. They do the easy one, then everyone has one of their own. Some will succeed, some will fail, and then they can present at least their successes in their blog. Now, the last thing we're going to do is a computation, and well, same computation twice. But I'll just pause there. Any questions so far? Okay. And we always want to try to infer something physical, whether we're making a pretty picture or an interesting sound file. What can we infer physically? And so what the educators came up with this for this module is the size of the neutron star. We can place a limit on the size. So I'm going to go over to my students. So, when I do this with my class, I put up the spreadsheet and here are the different teams and here are the different pulsars and here are the periods they're measuring and whether they detect polarization. So everyone succeeded with 0329. 2021 was successful. That's the one we just failed on, but it succeeded for them. Kind of a mixed result with these two. The two longer ones were off, but these two were on. We just did 09. Previously, we did 0950 there. Okay, so here's the math. Let me bring up Paint, maybe. So the math is real easy. Here we're looking at the neutron star from the top down, and it's spinning in some direction. Suppose someone's standing on the equator. What speed are they traveling? And their speed will be equal to the circumference divided by the period. Okay, that makes sense. So I'll go back here. There it is. Speed is circumference divided by the period. So circumference is pi times the diameter. So velocity is pi times the diameter over the period. And so the constraint is it can't be spinning faster than the speed of light. And it's a good constraint because neutron stars, the fastest ones get right to the breakup speed. So good fraction of the speed of light. So we'll apply the constraint. V must be less than C. So pi d over p must be less than C. So d must be less than Cp over pi if you do the algebra. So here, C is 3 times 10 to the 5. The period they measured, pi is pi. And they calculate it. And then for these pulsars they've done, we encourage them to put in Earth diameters because we're just doing slow pulsars. There's a reason for that. The fast pulsars, the analysis is much more complicated because of dispersion measure. Basically, high frequency radio waves bounce around electrons in the interstellar medium and come later. So each pulse, you get the low frequency stuff first and the high frequency stuff last. So the pulses go whoop, whoop, if you sonify them. And to correct for that and get the pulse period, very complicated. So for pedagogical reasons, we stuck with the slow pulsars where the dispersion measure is tiny compared to the period. You don't have to worry about it. Anyway, so these are slow pulsars, which means you're going to get kind of a weak constraint. And so instead of keeping it in kilometers, because neutron stars are about 20 kilometers in diameter, we have them converted to Earth diameters. And you can see, we tell them just do the fastest one you did as a team. And it's either going to be this one, or this one. And they get about, an Earth diameter or so. Here they're getting about 4. So they're placing a meaningful constraint that these compact objects are about the size of Earth or smaller. And it turns out they're a lot smaller. And for how much smaller, we give them some that have been dispersion measure corrected. So the tool that they're using can't do this dispersion measure corrections. We do have such a tool called Presto built into Skynet, but it's a total black box, just gives you the answers. So it didn't seem like a good way to go pedagogically. But in the module, what we do is we give them, bring the module back up. We come down to, I think it's page 13. Yeah, there are 3 of them here. And go ahead and download these. You don't even have to process them. They've already been period folded. Dispersion measure corrected and period folded. So I just save these 3. What's it doing here? Fit link. Oh, that's not it. Maybe I have to go here and then download it. Okay. So just grab these 3 right now. This is super fast. But keep them in order. That's the first one. Here's the second one. And they're so fun too. Oops, I don't want to open it. I just wanted to save it. Here, that button. There's the download. And the third one, the funnest of them all. Most fun. Okay. When you have them, you can go to your tool. And let's upload them sequentially. Okay, so that's the first one. So, it skips over the previous steps. It's been period folded because we had to do the dispersion measure correction. It's kind of fast. 0.14 seconds. Okay. Then they can listen to an even faster one. This one is 0.016 seconds and has an interesting pulse structure. And then the fastest pulsar ever discovered, 0.0013 or 0.0014. This thing's rotating 700 times per second. More massive than the sun, size of your town, 700 times per second. You can't even hear the pulses. At this rate, it is just a frequency. Yeah, I can tell from Brad's face, his volume is turned up. So, but it's fun when you teach this. They're going through their other pulsars and you're hearing chunka, 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 chunk throughout the class, or chunk, 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 chunk. And then they get to these and you hear psst, and they're having a blast, not with pictures, but with audio forms. And then with this one, we have them redo that calculation here, the simple calculation to place a constraint. And in this case, they keep it in kilometers, and I think they get 60 kilometers. And we know neutron stars are 20 kilometers. And we know this because there's another way to measure it. You look in the X-rays where there's thermal emission from the surface, and you can measure luminosity and temperature, calculate radius. And we know the diameters are 20. But this thing gives you a constraint of less than 60. So that means it's spinning at third the speed of light, something like that. So it's nuts. But that's the module with a few very simple calculations, but meaningful. I'll shut up for a few minutes. We have 4 minutes left. I actually finished early.
Dan, I have a question for someone who doesn't know a lot about pulsars. Can you talk a bit about like what's happening when they go on and off?
Well, that's connected to Calay's question from earlier, where I was like, no one really knows. So she was talking more about the pulses changing in brightness from pulse to pulse, and just sometimes that brightness changes down to almost nothing. And it's easy to say, it's an active field of research and no one really knows. And I think that's the true answer as well. But I'm sure the real story is more complicated. People who work in this field have leading theories, and I mentioned, the one that Chris Clemens produced based on white dwarf pulsations, where, let me put up the picture here. It's all about this hotspot right here at the top of the neutron star. These hotspots are ionizing the gas. And so then you have free electrons that can move through these fields. So what's making it hot is the question. And again, the mainstay of the field, as I understand it, is kind of a garbage model where they say there are kind of these 12 spots on the surface and they're going, I don't even know what's happening with them. The model that Chris put together, the idea is the hotspot was driven by radial pulsations. And it's been a long time, and just like on a white dwarf, has radial pulsations, and these things can go in phase and out of phase, and appear and disappear. And so, at least that was the beginning of a physical model, I thought. But again, I don't know if the field latched onto that or just ignored it. Probably ignored it because it came from a completely different field. White dwarf pulsations. Those are very different people than neutron star theorists and empiricists. But my understanding is there's no clear-cut explanation for what's driving this, but it happens right here at the hotspot.
Cool. Thanks. Sorry for repeating a question. I think I probably stepped away while you were talking
Oh,
about
okay.
that before.
Well, it wasn't exactly the same question. Clay was asking about why do they change from pulse to pulse, and this is just the extreme, changes to zero and turns off for a while.
But I always like it when I can introduce something that is like that they can understand in the first 5 minutes of in an intro class or relatively low level class and say, well, this is active research right here.
Mm-hmm.
I think that's sort of the fun way to
Well,
to portray it rather than like we're all so ignorant.
another way, along those lines is, all these students, MWU students, forevermore, at least on these six pulsars, are collecting a few minutes of data. And so, in theory, all this can be put together to study how pulses go on and off. People have to write proposals, garner a telescope, have a certain amount of time, it's scheduled. Here's just going to be a database, a really good database of pulse heights, little snippets, but at different times. Other comments, thoughts? Okay. Well, we're at 4 o'clock. So next week, we'll do radio spectroscopy, rotating edge-on spiral galaxies. We're going to weigh some galaxies. And Rachel saw this when she came to observe my class, and so she got to see this, and she can attest, at least for the one part, the visual part that we'll do. I think we got at least five. We heard this is so cool like 5 times. So I think you'll like it if you haven't seen it before. All right. See you next week.
Thank you.
Thanks, Dan.
Thanks,
Thanks.
Dan.
That was really neat. Bye.